Good morning, everyone. Am I audible clearly? Okay. So today I'll be talking about SSI, Serializable Snapshot Isolation in Postgres. My name is Vaijayanti Bharadwaj. I work for EDB. I work on Postgres distributed. So today's topic is about implementation of serializability in Postgres. And there has been some research in 2008. So the traditional algorithm for serializability has been strict two-phase locking, which is known for a long time. But in 2008, there has been some amazing research where you could achieve serializability on top of snapshot isolation without using a pessimistic algorithm, but a more optimistic algorithm. And this research was implemented in Postgres in 2012. And I was quite intrigued by this research and the implementation. And today I have, the goal of this talk is basically to look at the background of snapshot isolation. To understand the research, we will look at serialization dependency graphs, which help us understand transactions. We'll then look at the algorithm. We will look at its implementation in Postgres and some future work and summary. And we will see how this talk goes and how much in detail we are able to go into it. So I'll start with some background. So this talk assumes knowledge of transaction snapshots, MVCC, and we build from that point onwards. So snapshot isolation is is considered a pretty good algorithm for concurrency control, and we'll start with that and some of its limitations. So, so with snapshot isolation, every transaction sees a consistent snapshot of the database at the start of its time, and it keeps seeing that snapshot. Writers never block readers, and readers never block writers. So there's a lot of concurrency, and it's implemented via MVCC, and it's the repeatable read isolation level. So what are the limitations of snapshot isolation and what anomalies it prevents? So yes, it obviously prevents dirty reads because we don't see uncommitted data. We see the same transaction snapshot as we see in the beginning of the transaction throughout. So we get repeatable reads. There are no phantoms. Phantom anomaly is prevented. Phantom is when you could be inserting something while some query is querying it. You do not see what has been newly inserted. And lost updates. So we don't have lost updates because it locks the row being updated. So if another query is updating that row, it would block. And if the first transaction commit, the first committer wins. But what SI does not prevent is an anomaly called write skew. And this is when transactions read the same data, but they could be writing different data. And we'll see an example of this. So write skew occurs when two concurrent transactions, they read overlapping data. They read the same data, and based on reading of that data, they could be modifying different data. So because they modify different data, SI cannot detect this anomaly. So it misses this entirely. So we'll see an example here, which is very often seen in literature. So, we have on-call support engineers and the constraint that at least one engineer should be on call. So basically, we have transaction T1 where Alice is checking if somebody is on call, and yes, someone is on call, at least her and someone else is on call. So she sets herself off call and commits, and it succeeds. Concurrently, Bob is also checking if someone is on call, and yes, he sees Alice on call, and he updates and sets himself as off call. And both these transactions commit, and no one is on call. So this is the classic write skew. Both think it's safe to go off call, and under snapshot isolation, both these transactions would commit. So the ways that people could use to avoid write skew is We could artificially create a conflict by using select with for update, which will cause one of the transactions to be blocked till the other one completes. So the other way is to explicitly materialize the conflict by, say, forcing them to update the same row on a table, like creating a table on call count and have each transaction updated. Or we use the serialize, both of the first two methods require a knowledge of the application, and in an application with a lot of transactions, it's difficult, and in applications where we can have ad hoc transactions, that's not possible. So the safe way to do it is to use serializable isolation level, which guarantees correctness in all cases. So basically serializable means, just delving a bit into what is serializability, it means the result of executing concurrent transactions is equivalent to some serial schedule, which is one at a time schedule. And the key guarantee is that any application logic that works correctly in a single user mode will work correctly under concurrent execution. And there is no anomaly when you have serializability, no dirty reads, no phantoms, no write skew, no other anomaly. So, building onto how SSI is, like to build an intuition around SSI, we understand something called serializable dependency graphs. And this gives a better understanding of transactions. So this is basically building edges between transactions, considering combinations of all possible transactions which can run concurrently together. So assume that you have two transactions, T1, T2, they are concurrent. So T1 reads a record and T2 writes that record. So you have an edge called RW edge between them. And similarly, say T2 reads a record and T1 writes it. So you would have another edge between them. This is called RW edge as per SDG definition. And this is kind of modeling of the write skew that we just saw, which means that transaction 1 read some data and transaction 2 wrote it, and transaction 2 read some data and transaction 1 wrote that same data. So thus a cycle in SDG causes a violation of, causes a write skew under snapshot isolation. There is other types of edges. This is the WW edge, wherein T1 and T2 are not concurrent here. T1 commits before T2 begins, so T1 happens first. T2 sees its write and does another write. So T1 has written X1 and T2 has written another version of X2. So these two are not concurrent, and this is a write-write edge. This is another type of edge, which is a write WR edge. So T1 happens first and then T2 happens. They are not concurrent. T1 writes X and T2 reads that version of X, and because T2 can see what T1 has written, T2 takes its snapshot after T1 commits. So this is, so WW and WR edges are denoted with solid edges, and the concurrent, the first edge that we saw, which was when T1 and T2 are concurrent, is with a dotted line. So these are the three kind of edges in SDG. RW, where T1 and T2 are concurrent, T1 reads X and T2 makes its tail by writing to it, and WR is when T1 commits before T2 begins, and WW is when T1 commits before T2 begins. So we will use this to look at some examples. So basically, like I said, SDG considers every possible combination of transactions occurring together and draws edges between them. It is conservative. Those transactions may not be concurrent, but it can flag workloads as unsafe when the actual runtime conflict did not occur. And it means knowing all queries in advance, which is not practical for ad hoc queries. And use of a serializable, especially when you see cycles, possible cycles with SDG, you need to use serializability as the isolation level. So we'll consider a small bank schema. Workloads like PG bench are serializable even with snapshot isolation because they read the same row that they write. But this is an example which is not serializable, and we'll just describe it briefly. It's a very simple schema. There is basically a checking account with ID and balance and savings account, and just a mapping of name to ID. So we will model this with SDG. These are the transactions of small bank, and they are very simple transactions. Balance is checking, reading the balance of checking and savings account. Deposit checking is depositing something into the checking account. It reads the checking account and writes it. Transact savings is putting something into savings. It is reading savings and writing savings. Amalgamate is taking two accounts, and it is reading the checkings and savings of both and transferring them to the other and deducting it from the other. So it is reading checkings and savings and writing to checkings and savings. And write check is writing a check, but it deducts from savings. But if it sees that there's an overdraft by reading both the checkings and savings, that the check amount is not enough to cover both, then it will deduct a penalty. So these are simple transactions, and we'll just draw a graph to explain. So I've just represented the transactions here. Balance is a read-only transaction. So I have considered all possible occurrences. So when you see this arrow, it means it basically is a it's a WR edge because balance reads it between DC and balance. And because DC and balance can be concurrent, it is balance can read something and DC can make it stale. There is a RW edge. So similarly, balance and WC, balance can read something which WC makes stale. There can be a edge, and there can be a WR edge between WC and balance. Amalgamate and DC, they both modify, so there are no dotted lines between these. There are only solid lines, which means that they are serialized. They have to be serialized when they happen. They are modifying the same rows, and they only have these solid arrows between them. So I'll just go faster. The same is with DC and WC, only solid arrows because they get serialized. Same with, so because TS is, WC is reading savings and TS is modifying it, there is a dotted line between them. Amalgamate and TS are fully serialized because they read and write checkings and savings. Similarly between balance and TS, and so this is, so this is the complete SDG. And if you, so by the way, you can never have a cycle with solid edges because the transactions are committing one after the other. It's just a way of denoting. But if you see here, the only cycle here is between balance, WC and TS. And it is very ironical that it's the presence of a read-only transaction which makes this workload non-serializable. If you were to take out the balance, this workload is serializable even with snapshot isolation. So that was a paper, topic of a paper written by Alan Feckett as part of this research, that a read-only transaction can cause an anomaly under snapshot isolation. And we'll look more at what this cycle is. So if you take this out, this workload is completely serializable under SI. So what is the anomaly here? What is the cycle here? We'll just see. So essentially, I mean, just to give an example, you can say that initially you have 0 in your savings and checkings, right? And you write a check, let's say WC writes a check of $500, and let us say that at the same time the salary gets deposited, but the depositing of salary, which is TS, and WC, the writing of the check, are concurrent, so they don't see each other. So WC will let you deduct $500, but it will add a penalty to 500 and it will deduct 550 because there was no addition in the savings. But the thing here is that balance sees something contradictory. It sees committed, the solid line means it sees the committed result of savings, the savings account being credited. So it will show 500 as the savings balance and 0 is the checking balance because it has not seen the debit of WC. So somebody looking at who has executed balance will really wonder they will see a debit of 550, they will really wonder why I was charged a penalty when I have already, my balance already has $500. So there is no order that you can give to these transactions. You cannot say that WC balance did not see the result of WC, so balance came later, but it saw the result of savings. So you cannot, there's a cycle, you really cannot say which order they occurred in, and that is what the cycle refers to here. A cycle in SDGs indicates a serializability violation. In the on-call engineers example we saw, there were just two transactions there, and T1 appears to have executed before T2 and T2 appears to have executed before T1. So there is no serial one at a time execution that matches the actual execution. Coming to the SSI algorithm, so we look at, so we have developed some intuition about cycles, and we look at what the algorithm says. Before that we look at, this is just a slide to give context on strict two-phase locking, which is how serializability is implemented in most databases. So it's a pessimistic algorithm. Every transaction has a growing phase where it acquires lock, and a shrinking phase release locks, which is typically just transaction commit, you release locks at commit. All locks are held till transaction commits, and you even have read locks which allow multiple readers, and exclusive locks block everything. And there are range and predicate locks. So if you do a query, you say that increase the salary of all employees where city is Pune, and a Pune employee gets added, the added employee will not, the range is protected and the added employee will block till the query executes. So the lock ordering gives a, because you have an ordering, you are forcing a commit order which is consistent with the serial schedule. So the transactions in which the order commit is the transaction in which the serial schedule sees it. In contrast, we are looking at SSI, which is a more optimistic algorithm, and it is based on the observation that every cycle in the graph that we saw needs to have two adjacent RW edges. And in addition, one of the transactions, we call the presence of two adjacent RW edges as a dangerous structure. And in addition to the presence of the dangerous structure, one of the transactions the T out transaction must commit first. And detecting this pattern is enough. We do not have to detect the entire cycle, because detecting the entire cycle can require a lot of tracking and can make this algorithm infeasible. So basically, this algorithm says that you can execute at snapshot isolation, but whenever such a structure is detected, you abort one of the transactions, and that is how you get serializability. So transactions get the benefit of snapshot isolation, and we conservatively abort some transactions which can possibly give us violation. The intuition, there are papers which have the formal proof behind this, but the intuition here is that for the cycle to complete, there has to be either a WW or a WR edge back from T out to T in. And the only way, as you remember, WW and WR edges were when one transaction commits and the other sees the results of that. So for that, T out has to commit. And if it doesn't commit, there is no danger of it being a cycle. So that is the algorithm. And essentially, it means that we create a tracking structure for every transaction. SSI essentially is about modifying a few points during the transaction's life cycle. Begin initializes the tracking structure this is when the snapshot is taken. Read takes, every read that the transaction does takes SI read locks on the data read and looks for dangerous structure. Every write checks, are there SI read locks on the data I'm writing, and looks for, we will see more visually how this happens. And commit does a final check for the dangerous structure. So these are the points at which we check for the dangerous structure, and we abort a transaction when we see it. So basically on begin, if you think of, let's say there is a tracking structure which we initialize when snapshot is taken, and we have an out conflict and an in conflict field which can be thought of as an edge. So T1 has an out conflict and in conflict. I have denoted it here as a bool, but it's actually a pointer to a transaction, another transaction which is outgoing. And it could also be a list of out conflicts as how it's done in Postgres. So you initialize these. On every read, we acquire an SI read lock. We'll talk more about what is a SI read lock on the data. We check if the data was written by a concurrent serializable transaction. So while reading, if we find that the data has already become stale because a concurrent transaction has a more updated record, we know that we will mark out conflict as true and T1's out conflict as true and T2, the other transaction, in conflict as true. Similarly, on every write, if we find that the record has a SI record or relation, whatever has a SI read lock, we say we mark the in conflict fields and every time we mark these fields, we check for a dangerous structure. Dangerous structure means if I have an in conflict set and out conflict set as well, that means that's a dangerous structure. And finally, we check for it at commit time as well. So SSI in Postgres, and we'll take a look at how these tracking structures look like. There is something called a serializable exact maintained for every transaction. And this, if the isolation level is serializable, when you take a snapshot, this is initialized. And basically, it tracks a lot of things. But most importantly, it has a list of out conflicts, which transactions whose writes I did not see, and in conflicts, transactions whose reads missed my write. So this could be a list, and it is a list of other serializable transactions. There is a list of SI read locks. SI read locks are also predicate locks, which this transaction has taken, and the state of where this transaction is. So SI read locks are serializable isolation read locks. These locks are maintained in a parallel, I mean, they are not in the same space as the conventional locks, the heavyweight locks in Postgres, which are managed by the lock manager. These locks are managed by the SSI machinery. And these are basically they're non-blocking. So even when a transaction commits, the locks continue to be held because the locks continue to be held till all concurrent transactions have drained out. So this makes it interesting because they could continue to take up space, and there has to be a mechanism of ensuring that all of these structures are cleared away. They are right now at multiple granularities, tuple, page, and relation. Consolidation to a coarser granularity is done with the help of these GUCs, like max predicate locks per page, max predicate locks per relation, and per transaction. If T locks a tuple for writing, like if a transaction modifies the same row that it is reading, the lock on the tuple is removed, the SI read lock goes away. So index scans for each leaf page scanned, the index page is locked. Whenever a heap tuple is fetched, the tuple is locked. Sequential scans lock the entire relation. Page level locks on index pages serve as gap locks. So for example, if you're searching for a certain range and you read a like a bunch of pages, leaf pages, all of those would be locked, and everything on those leaf pages is considered to be locked. So any future inserts happening in that range will also be locked. So page level locks on heap tuples are only used to aggregate tuple level locks. They are not gap locks, whereas page level locks on index pages serve as gap locks. So we'll see an example of our support engineer example that we saw earlier. We have transaction T1 where we are selecting where Alice is checking whether there are engineers on call, and there is a select count star here. So this is a scan, and similarly T2 does a scan. So we'll see the SI read logs. This is how they look like. There is, we have SI read log taken on, this is output of PG logs, and because we scanned the relation, it's a relation level log which is taken. Now Alice updates to say that she's off call, and after this update, I'm just showing this is how the, because she sees after this update we have an edge going from T2 to T1. So at this point, the update will notice that there is already an SI read log taken on the row that it is updating, and it will mark the in conflict of T1 and out conflict of T2. And similarly, we see that, so we see the SI read log on the page taken, and because we scan the page and we take that SI read log. Now T2 will also update it, and we see it's we see that these are the edges which are marked in the tracking structures, and there is a cycle at this point, but no transaction at this point is aborts, and that's because nobody has committed yet. And now, yeah, this is the log taken by the T2 as well on the page. Now T1 commits here, but still we allow T1 to commit, and why is that? Because we don't know if T2 will be reading more records, because it's possible T2 is a long transaction, and if it reads more records, the next call into the SSI machinery will kill T2. So we are we don't want to prematurely abort something. For all we know, T2 could roll back as well. So we let T1 commit, and T1 commits T1 commits first. And now when T2 commits, the commit has the check that there is a dangerous structure and T2 committed. So you get this error, and with a detailed reason code that cancelled on identification as a pivot during commit attempt. So this is how serialization looks like in Postgres. Now read-only transaction optimization. How much time do I have? Okay. So read-only transaction optimization. Now you can have long read-only transactions, and they can keep accumulating a lot of SI read logs, and you can run out of space. So if we know that there was nothing concurrent with a read-only transaction, the read-only transaction can execute with snapshot isolation. And but if there are concurrent transactions which are writable, then the read-only transaction has to track them if there is a potential conflict later. So in the serializable exact that we saw earlier, there is a list of possible unsafe conflicts. So R maintains, R the read-only transaction, maintains a list of possible unsafe conflicts with every concurrent read-write transaction, and every other read-write transaction which was concurrent with it will check whether it made R unsafe by checking that was I writable, did I commit, did I have a conflict out. Basically we are seeing if the read-only transaction has a conflict out to this transaction, and which in turn has a conflict out, and did that conflict out commit before R took its snapshot. So if none of these is true, we remove W from the list of R's the possible unsafe conflicts list, and when it is empty, R can stop taking SI read logs and proceed as a normal transaction at SI. We can have deferable, so certain transactions like PGDUM can take a really long time to execute, like a full day or something, and we do not want it to be accumulating SI read logs. So it can be declared as deferable, means wait to take its snapshot till all concurrent read-write transactions drain, and you can declare it as read-only deferable, which means defer my snapshot, I'm okay to wait for my snapshot. So it starts, instead of starting immediately and having to opt out later, it blocks until the snapshot is proven safe. Now, you could accumulate a lot of SI read locks. You could accumulate a lot of serializable transactions. How do you kind of condense this? So when no more serializable exact is available, we summarize it. So there is a pre-created list, and when it exhausts, we grab the oldest one from finished serialized transactions is a list where we put them back once they are finished, but if there is none remaining in this list, we start, we could have, so we have an SLRU, which is the transaction ID. It only has one field other than the transaction ID, which is earliest out commit conflict, and we'll see why that's needed. So we just keep these two things out of the entire serializable exact and move it to a SLRU. SLRU is a data structure in Postgres which is indexed by something which is increasing in order, and you keep the least recent, you move the least recently used to disk, and it transfers all the predicate locks which were held by this serializable exact. They are transferred to a dummy serializable exact, and duplicates on the same target collapse. So basically, R represents a transaction, S is the summarized transaction. So what we are only saving, so whenever we encounter a dangerous structure, if R, did S have a RW conflict out to some committed transaction, and if R is not RO, the earliest out commit conflict on S being set is enough, but if R is read only, then earliest out commit conflict will tell if RO committed before, will tell if T2 committed before R took its snapshot. And the other case is when R is the pivot. In this case, we don't need, we just need to know that S was committed, which it is. So coming to summarizing our entire discussion so far. So snapshot isolation is not serializable like we saw. Workarounds for consistency do exist but are fragile, and if we want to have ad hoc queries which potentially could have cycles, then use of serializability is important. SSI provides two serializability. There could be false positives, but there are no false negatives. Postgres implementation is production grade, and we do have multi-granularity predicate locks, memory management, summarization, and optimizations for read-only transactions. The dangerous structure theorem means that we need to track read-write conflicts between concurrent transactions, and we don't have to build a full dependency graph, but using dangerous structure theorem can cause false positives under load. This is especially aggravated when we are promoting locks, which can happen with memory exhaustion. Also, the SSI GUC values, the defaults, and a lot of the SSI structures are statically allocated, and they have not been revised. They are considering I mean, the GUCs could do with more tuning, and the structures could be more dynamic. So these things could be done to improve SSI. So with one of the things with SSI is that all transactions need to be run at serializable isolation level, because like we saw, the SSI machinery is separate, and just running one or two transactions which are pivot transactions, like the balance transaction we saw at SSI, is not helpful. It will not detect violations. As against this, perhaps in strict 2PL, strict two-phase locking, we could perhaps have a mix of transactions running at different isolation levels to give us serializability. A future work, one of the major things is about reducing false positives, because SSI gives pretty good amount of, as you increase the concurrency and load on the system, you can get a lot of false positives. So tuning lock promotion so that more fine-grained locks can be taken for longer. Then optimizations for predicate locking. Like we saw in that example of the on-call engineers, it can happen that even a unique check using equality on all columns of a B-tree index should not cause us to take a predicate log on the index. So we were seeing a predicate log on the page even though we were checking for a precise value in that index. So a B-tree scan of, for example, less than 200 can end up predicate locking pages 3, 4, and 5. And a concurrent insert on page 5, even if it is 999, will cause a conflict. So there is a lot of room for false positives and scope for improvement here. Also, not all indexes support predicate locking with SSI. There is work needed with monitoring and statistics. SI read locks appear in the PG logs view, and the reason code shows detailed reasons such as this and many more, telling us what caused the cancellation. But there is no visibility into the serializable entries, like for example, at that point, one of the that we saw with the on-call engineers. So yeah, these are some of the shortcomings today, and I'm almost at the end. So yeah, that's about it.